Always cold? Would you ever turn the fan off? No? Okay. Let's see. We got this far. When the bell rudely interrupted us, we were in the process of trying to write our primary equation, which is, again, the equation that we're going to be working with, the one that we're trying to actually optimize, in this case, maximize. We want it to be in terms of a single variable, because that's what we know how to do. We're still on the ground level when it comes to calculus. There's multivariable calculus, and most things in the real world have many different variables that affect its outcome. But we're training with just one variable at a time. So the question is, it doesn't matter if it's in terms of C or B ultimately, but I need it to be in terms of one variable. So how are we going to do that? Here's the thing. Every single optimization problem is going to have, again, and what I mentioned, some constraint, something that's going to prevent you from making the product, in this case, as large as possible. I mean, if you wanted to make this product as large as possible, and that was all I told you, you would choose like C equals a kabillion jillion, and B would equal a kabillion jillion billion, right? And square it, right? And then you could go even bigger than that. In fact, there is no upper bound to this product, right? But there is one little catch here in our situation, because we're trying to find the largest product of the two numbers whose what? Their sum is 60. Woo! That kind of narrows it down, right? So, what? Maybe so. Maybe 1 times 59 squared is the largest, right? Maybe 2 times 58 squared is larger because you're doubling something. I don't know. That's why we're not going to do trial and error. We're going to do it systematically with using calculus. So here's the thing. The constraint equation doesn't necessarily have to come second or first. It just has to come if you have your equation over here in two variables. So if we're calling the two numbers B and C, then according to our constraint, B plus C must equal 60. Do you agree? All right. Now the constraint equation is always then going to be the key for getting your primary equation, your optimizing equation, in terms of a single variable. So here's what you do next. You can solve this constraint equation for either C or B. It doesn't really matter. Then you're going to plug it in over here for either C or B, whichever you decide. So make it easy on yourself. This equation here is just as easy to solve for both C and B. Would you agree? Yeah. But what you're going to be doing then is plugging it over here. Do you want to square what you're plugging in or not square what you're plugging in? Thinking easy, not square. Yeah, I don't want to square either. So I'm going to solve mine. Based upon that, I'm going to come over here and solve this for C. Truthfully, it doesn't really matter. But if I solve for C, I get 60 minus B. This right here, you're going to want to box it and put a star by it, because you might come back and use this. When you plug in over there for C, you're going to get an equation in terms of B, which means you're going to find B first. If you need to come back then and find the other variable, in this case C, this is what you're going to use. All right, but for now, we take our primary equation, and every time we see a C, we're going to put a 60 minus B in there. So we get 60 minus B times B squared. Now, I'll tell you, last period, we did B times C squared. And it didn't matter. We're going to come up with the same answer. Because if you keep it then consistent all the way through, whatever you're calling B and whatever you're calling C should work out. All right. This is the part now where we have it in terms of a single variable, where you want to think, if you haven't already, you want to think of a relevant domain. What values make sense? Well, we already said that B has to be between 0 and 60. It can't be 0 because 0 is not positive. 60 is positive, but if one of them was 60, the other one would have to be 0, which is not permitted. So really, our value of B has to be somewhere on the open interval from 0 to 60, which means the EVT doesn't apply. Now, I'll show you how we're going to get around that here soon enough. If I then have no endpoints, it turns out that the values that optimize the quantity you're looking for, if they exist, are going to have to end up being where? On the open interval existing at, if they're not at endpoints, they have to occur at critical values. And how do we find critical values of any function? We take its derivative, and then we set it equal to 0. Okay, so if I'm going to take the derivative of this, maybe without using the product rule, I'll just distribute first, and I get 60b squared minus b cubed. And it's a polynomial. Nice, a cubic polynomial with a negative leading coefficient. Here we go. P prime is 120b minus 3b squared. Is this ever undefined? No. And it turns out when you're looking at like physical quantities in the real world, the critical values that make the derivative undefined, not always, but typically, at least at the level we're at, those values aren't the ones we're looking for. Okay, that would be like having a slope of infinity, which means infinity miles per hour. It doesn't quite make sense. Okay, so we're going to be looking primarily for the critical values where the derivative is 0. And then once we set it equal to 0, we look for a common factor. So if I factor out a 3b, I'm left with 40 minus b. And of course, then I get my two critical values of my cubic polynomial to be 0 and 40. Now here's the deal. Those are definitely going to be horizontal tangent lines on my cubic function. But sometimes you get more critical values than you need. Some of them might be in the relevant domain. Some of them might not be in the relevant domain. Are both of these in our relevant domain? 0 is not. Okay. Now, if you did end up with two critical values in your relevant domain, which could happen, one of them might be a max, one of them might be a min. They might both be local maxes, and then you need to see which one is actually bigger. So if there's more than one critical value, you're going to need to test it out. Now, here's the result. We know that the open interval doesn't exist. We know we only have one critical value that makes sense. We know there has to be an answer, right? There are going to be two numbers where the product is going to be the maximum. Because if you plug in 0, you get 0. And if you plug in 60, you get 60. And so to go from 0 to 0 with positive in between, it has to go up and it has to come back down. So we know there has to be an absolute max. And if it can't occur at an endpoint, and there's only one critical value on the open interval, guess what? We know our answer without any type of analysis by process of elimination. Now that on a multiple choice question might be good enough. And 99 times out of 99.5, when you do optimization problems at this level, you'll probably end up with a single critical value, and that critical value most of the time will be the value you're looking for. Every once in a while, it could be an endpoint on a closed interval, and we'll look at some of those. So if it was a multiple choice question, you wouldn't have to justify. But I do want to kind of get you into the idea of justifying when you don't have a closed interval, because that's what makes optimization potentially kind of arduous, the after-the-fact stuff. If you look at our product equation, it's a cubic polynomial with a negative leading coefficient. We know from our Algebra 2 pre-cal polynomial days that that's going to look something like that. The end behavior is negative infinity as you go out to the right. It's going to have two turning points. I know that this 0 is one of the horizontal tangents. Being less than 40, that means that this must occur at x equals 0, right? And that means that this must occur at x equals 40, right? Now, what do you get when you plug in a 0 into this function up here for p? You get 0. So not only do I know the y value there, I know, or the x value, sorry, I know the y value. So this is actually an x-intercept. It's going to look something like that. So in our relevant domain, notice if I were looking for truly just all numbers, which is why I needed to add positive in there in the beginning, if I was truly looking at all numbers, does this cubic polynomial have an absolute maximum? Now, if I'm allowed to use negative numbers, this goes up forever. There's no absolute maximum value. Similarly, if I go out to infinity, there's no absolute minimum value, okay, because it goes down forever. But if I'm looking on my relevant domain, which guess what the x-intercept is right there? It's got to be 60, because when you plug in a 60, you get 0. So my relevant domain is really just looking on this open interval. And even though I can't use the closed intervals, because I'm just looking on that open interval, I can see clearly now visually that on that relevant domain, at 40, there is not just the local max, but on my relevant domain, it is also the absolute max. Now, here's what you'd have to say if you had to justify it. You declared your relevant domain from 0 to 60. You can't just say the product has an absolute maximum at x equals 40, since p prime changes from positive to negative at x equals 40. Because when you say it changes signs at x equals 40, you're saying immediately to the left, p prime is positive, and immediately to the right, p prime is negative. And that's a what type of argument? It's a local argument. It's a relatively small argument. It's for a local min. Here's what you'd have to say, and we'll practice this later on. You'll have to say something like this. P is maximized, which means absolutely, right, at x equals 40, since p prime is negative, but not just immediately to the left. P prime is negative for all x between 0 and 40, and P prime is negative for all x's between 40 and 60. So what that means then is on the values that make sense, this graph is not just going uphill immediately to the left, it's going uphill everywhere to the left, which means it has one thing to do and one thing only where it lives from 0 to 40, and that is go uphill to some high point, after which it goes down forever over the relevant domain. So when you say that P prime is negative everywhere to the left, and P prime is positive everywhere to the right, everywhere is no longer a local argument, right? Everywhere is an everywhere argument, right? On the interval that makes sense. That's the only difference. That's using kind of the first derivative test as an absolute max. All right. So we have the optimal value at 40, which I guess for us is not x. We've been calling it what? B? What do you do with your answer now? You box it and walk away? 40? No. This is a word problem. And it's going to ask you for something very specific. So what you need to do then at the very end is just, after you've possibly justified, you need to answer the question. Was it looking for one of the numbers? Was it looking for the other number? Was it looking for the actual product? Well, let's come back up here. Find the two numbers. We found one of the numbers. So here's what you can do. Answer the question. So the product is maximized when... Now, it's important here that you say which letter is which. You can't just say the two numbers are, because it matters which one you're squaring. So now you'll say when B equals 40 and C equals, how do you find the other number? Right. The one that you plugged into is ready to go. Plug in a 40 for B, and you get 60 minus 4, which is 20. Now, 40 and 20 might be the first two numbers you think of, maybe, when you think of partitioning 60 into two numbers. Y'all didn't mention that, because you were probably thinking now it wouldn't be the obvious one. But in this case, it does turn out to be 20 times 40 squared. And we know that without having to do any trial and error. 20 times 40 squared is the largest product you're going to get for any two numbers that add up to 60. That exhibit that behavior, AB squared. Or whatever y'all did, CB squared, CB squared. Now, what if the question asks you for the actual product? You wouldn't need to have to say that. You take your optimal quantity, and you can either find the other number on your own and then do 20 times 40 squared, or this equation or this one here are also both useful because they give you the quantity that you're looking for in terms of the variable that you have found. So you wouldn't need to find the other value. So if you plug the 40 in right here, you get 20 times 40 squared. 40 squared is 1,600. Yeah, 1,600, 1,600 times 20, 32,000. Yeah. So you would then say, so, not in highlighter, maybe afterwards. So the maximum product is 32,000. And then, as I said, maybe not erase it. Ooh, they're close. Highlight. So answering the question is the final part. You don't want to just box the first number you get. The optimal quantity that you find will then allow you to answer the question. Just make sure you find specifically what it's asking for. That problem right there contains the entire anatomy of any optimization problem you're going to work, hinting at the possible justification. When you get an optimization problem, you're really, really hoping it shows up on a multiple choice, because then you don't have to justify. The justification is somewhat tedious, because you have to write sentences. But it's not that bad. Y'all could do this, right? Other students find it a little bit difficult to make that orange juice from the oranges. You have to write your own equations sometime. You have to define your own variables, which could be anything, and you have to write your own equations. So, and that's kind of what the real world primarily is. You just don't go shopping for an equation on the equation aisle at the Super Target or the Dollar General.
Make your own juicer if you want it.
It's the best kind. Yeah. Or you just go to the H-E-B where they make it fresh in front of you, you buy it, and you pay a premium, and you say that you made it at home. But you see, they're squeezing it right in front of you. And they use kind of the reject oranges. Have you noticed that? But it still tastes pretty good. Imagine if you bought premium oranges and squeezed it. Yeah.
You gotta buy the machine they have.
That's a nice, yeah. All right. Let's try example 2. Okay, an 8-inch long pipe cleaner. You know what a pipe cleaner is? Not many of them are used for cleaning pipes, right? Not many. They do make pipe cleaners for cleaning pipes, but if you go to like Hobby Lobby and you ask for pipe cleaners, they'd be like, "Are you a plumber? You have dirty pipes?" No, they'll just say aisle 5, right? And they come very skinny. They're all different lengths. They're all different flavors, right? Beautiful colors. Some are sparkly, and very few people use them for cleaning pipes. Maybe if you have like a mouthpiece in your band, you use a pipe cleaner, or maybe you use like a fancy one, a toothbrush, right? Yeah. Anyway, we're going to use our pipe cleaners not to clean pipes, but to form rectangles for a calculus class. Yay! Or make calculus ninjas. There you go. Now, just looking ahead, later in the week, sometime this week, I'm not going to tell you when. It's not today. Today's National Mutt Day. But coming up on either Thursday or Friday, it's National Ninja Day. I kid you not. It's National Ninja Day. And we might have a calculus ninja come visit us. Yeah. Is he already here? I don't know. Here we go. What we're trying to do, we're going to take our 8-inch long pipe cleaner, y'all, and we're going to bend it into a rectangle. And the rectangle that we end up with, we want it to have the biggest amount of area possible. We want it to be the largest area. So there's your clue that it's going to be optimization, right? Maximum area. Well, I can do trial and error. I can make one of my rectangles kind of not very tall, but kind of long. I can make one that's more squarish. I can measure all of them, figure out what the area is, keep that running list, right? And then, is that the best way to do it? No. Okay. What we do want to do in this case, we have a geometric figure that we can draw to help us. In the previous one with the numbers, we couldn't really draw anything. So sometimes drawing a picture is really the first step. I know that the 8 inches is my restraint. Would you agree? My constraint? I can't make a pipe cleaner rectangle that is 100 feet by 1,000 million feet because the pipe cleaner is only 8 inches long, and that's going to end up being the what of each of my rectangles? The perimeter. Good. So my constraint is that the perimeter, which I'll call P, has to be 8 inches. Now I'm trying to maximize the area. The area of a rectangle is the product of the two dimensions, which we do not have labeled. So here we go. Both the perimeter equation and the area equation require 2 side length variables. What do you want to call them? A and B, L and W? L and W? Okay, so W and L or W and H or whatever. It doesn't really matter. Just make sure they're different. Because it won't necessarily be a square, will it? Okay, so here we go. The primary equation then is L dub. And now I got to get that equation in terms of a single variable. Well, my constraint is 8 inches, which I could say that's 2W plus 2L equals 8, yes? That writes the perimeter in terms of W and L. Now I get to solve the constraint equation, the perimeter equation, for either L or W. This one looks just as easy to solve for either one, right? So looking ahead to what I'm going to be doing with it, I'm going to plug it into LW, both of which are just as easy to multiply one times the other. So here's the rare case where it doesn't matter which one you're solving for. What would you rather solve for? W. Okay, so if you solve for W, you get 2W equals 8 minus 2L. If you divide through by W, you get 4 minus L. Box it up, come back to that. Now realize that when you're solving for W, you're going to be plugging W into the equation over there, and you're going to be getting rid of the W. Are you okay with getting rid of W? Yeah, no 4 more years? George W. So we got L times W, which is 4 minus L. Mathitude. All right. We've got the area equaling that. Since we have the area now in terms of a single variable, this is a great time now to think of a relevant domain. Relevant domain. For L, right? L has to be, let's see, the pipe cleaner's 8 inches. What's the smallest L could be? 0? Not quite 0. If you let it equal 0, then the height would be 8. And you have not a rectangle at all. You have what's called an 8-inch long pipe cleaner. Right? You haven't bent it at all. So would you argue that we could let it equal 0, in which case we'd have a minimum area of 0, because we only have one dimension? No, I don't think so. Oh, volume or area? Hmm? All right, what would be the absolute longest that the length could be? Yeah, you could. I mean, 8 would be a safe upper bound, right? You might be able to say, well, if you got to bend it in half to make a rectangle, maybe 4 even, right? But 8 would be definitely safe. The pipe cleaner is only 8 inches long, and of course, we're not going to include 8 because if it's 8 inches long, then it's 0 inches high, and you have an 8-inch long pipe cleaner again with 0 area because you get 1 dimension. I don't know. You can reason that, right? If you really had to make a rectangle, then you'd have to like take the length, you have to double it over to get back to where you started. It couldn't be 4 either. Yeah. So my point. Ooh, careful. My point is that as long as you come up with some relevant domain, you might be able to tweak it and come down with something narrower. But this is a safe one. This is safe. Okay. Notice though we don't have endpoints, so the closed interval argument's not going to work if we have to justify. Which means that the optimal value, if it exists, is going to occur not at an endpoint, but rather at a critical value on the interior. How do we find critical values? Derivative equal to 0. You want to use the product rule for the derivative? Me neither. Yum. So if I distribute, I get 4L minus L squared. Hey! The area formula is a parabola that opens down, bless you. On any domain, a parabola that opens down is not only going to have a local max, that local max will also be the absolute max on any interval. That's awesome. That's pretty cool. All right. I'm so excited I could barely finish the problem. Hold it together. Whew. A prime is 4 minus 2L. Is it ever undefined? No. Not that if it were, we'd be interested in that one for these real-life applications. We set it equal to 0, and we get 4 equals 2L, and so L equals 2. Closed intervals, not there. We have an open interval. Endpoints don't make sense. We have one critical value. Is it on the interval? Yeah, it's less than 8, and you know what? It's also less than 4. Okay, so again, it falls within our relevant domain. Now again, 99 times out of 99.5, if you have one critical value on an open interval, it's going to be the value you're looking for. Local min instead of a local max. What does our graph look like? Concave down like a frown everywhere, right? So you can do a modified second derivative test. You could say the first derivative argument would still look like this. If we're looking from 0, let's say 0 is right here, on the interval from 0 to, what was it? Oh, critical value is at what, 2? Yeah. So everywhere from 0 to 2, A prime is positive. And everywhere from 2 to our value is 8, which would be across the x-axis, which is fine, A prime is negative. The key word is everywhere, or for all x. That makes this value the location not just of a local max, but of an absolute max. Now notice because the curvature is concave down everywhere, the second derivative test can be modified as well. You could say the area is maximized absolutely at x equals 2 since A double prime is less than 0 for all, what variable did we use? L from 0 to 8, which would not be a lie, would it? So that's an absolute second derivative argument. Concave down everywhere on our interval, which remember the second derivative test, that means that the critical value is an absolute max now, not just a local max. Woo! All right, so we box it and move on, yeah? Whoo, no. What's the last thing? Yeah, right, just what kind of sentence? I will not forget to read the instructions on an optimization question. I will not, yeah. Those sentences will help you because that's what we need to do. We need to make sure we're answering the question. It asks us for the dimensions. Okay, so we found L is 2 and W is what? Well, we plug it back into here and we get 4 minus 2, which is 2. So in this case, since they're the same, does it matter which one we call L or W? No. But if they weren't the same, it would matter which one we call L and W based upon what we define it. So you would say, let's go ahead and write the sentence. the maximum dimensions, or the dimensions of the rectangle whose area is a maximum. You could write all that. The maximum dimensions is fine. Are L equals 2 inches. Make sure you put units by W equals 2 inches. Now, in this case, you could, because they were the same, you could just say R. There we go. You could say 2 inches by 2 inches, because then there would be no ambiguity as to which one's which. Now, of course, the rectangle whose sides are 2 on both sides is actually a special rectangle, right? Called a 2 by 2 rectangle, also known as a square. Does it surprise you that the most optimal rectangle is a square? No, it shouldn't. Nature loves symmetry. And very often, things that are symmetric kind of expand as much as they can in all directions when there's no constraints. And this is a rectangle, so it can expand horizontally and vertically as much as you can. Guess what the most efficient ellipse is? A circle. Yeah, very optimal. Yeah. No, they weren't in example 1, were they? The two numbers were different? Yeah. No. They can be different. Now, the way I've defined this problem, I did make them to be the same because I did want to talk about them being the same. Nature loves symmetry. But I could have said find the dimensions of a rectangle whose width was twice the length, was a maximum. Then it probably wouldn't be equal because it can't be, right? So it depends how the problem's defined. Guess what the most optimal triangle is? Equilateral triangle. And by optimal, I mean that it's the largest enclosed space per any given perimeter. That's what I mean by optimal. And you can do the same thing for volume, too. It's kind of interesting. Nature loves symmetry. Huh? Yeah, the most efficient polygon is a regular polygon where all sides are the same. Yeah, same thing. It's a trade-off between area and perimeter. And if you look at the buckyball that is at Epcot, it is the most optimal three-dimensional shape. It's a sphere, of course, but it uses tetrahedrons that make up the space. And it's optimal. Buckminster Fuller designed it. It is not only the most space per materials used, it's also, he optimized the strength. When you use tetrahedrons to join the surface, that gives it a certain rigidity that withstands outside pressure. And he believes, it's funny, he believed that the whole world would be filled with these geodesic domes, as he called them, these buckyballs, these Epcots, and that he thought that they were so efficient that if you were to construct them, they would defy gravity and they would float. That's how efficient he thought they'd be. And so he imagined all these cities in the future built inside these geodesic domes that were levitating. Wow. Wow. You think Nikola Tesla was cool with his ideas? Look up Buckminster Fuller if you're looking for a weird guy with interesting ideas. Okay? It's Epcot, though, right? Have a great, fantastic day.
Did you record you talking about Epcot?
I did.
Not edited out?
I will not edit it out. I'm a Disney fan.